So here's an example. Press pause and take as much time as you need to work through this on your own. Do your best. And then when you want to go through it with me, press play again. Okay, so here's my clock. The radius I was told was 0.5 meters. And let's just start first by understanding what is this term angular displacement. Okay, angular displacement, well, I know what my angular position is. That's that theta that we just defined. Angular displacement is going to be delta theta, just like our displacement before, just displacement on its own was delta x. Now when we talk about angular displacement, it's going to be delta theta. That's just theta final minus theta initial. So let's try to figure out what is theta initial and what is theta final. So we're starting at the 6. We always measure our angular position with respect to the horizontal, to the positive x-axis. And we always are going to be going counterclockwise when we measure that angle. So this is where the beetle initially starts. It's at the 6th position. So I need to figure out what is this angle that goes from that positive x-axis all the way around to here. What is that angle? Just in terms of degrees, I can tell that's 270 degrees because up to here would be 90, to here is 180, to here is 270 degrees. But I need this to be in radians, so I'm going to convert between degrees and radians. And the conversion factor that I like to use is that a full circle is 360 degrees, or 2 pi radians. So that's what I'm going to use as my conversion factor. I put the degrees on the bottom, so the unit of degrees will cancel. And I have radians on the top, so that's what I'll be left with. So mathematically, I'll do 270 times 2 pi divided by 360. And I get 3 pi over 2 radians. This is how you probably write it, in a math class where they care about pi. I don't care too much about pi. I like to just have numbers. So I just put in my calculator 3 times pi divided by 2, and this is the number I get. So this represents the initial position measured as that angular position is 4.71 radians. That's my theta initial. Now, my theta final is going to be when it's at the 9. So that's going to be over here. So now this is the angle that I'm looking at, which I think is pretty easy to see. That's 180 degrees. But again, I want to convert that into radians, so I use the same conversion factor here. And I get that that's equal to pi radians, or 3.14 radians. So now I have my theta initial, my theta final. I can calculate my angular displacement just by taking the difference between those two. So theta final minus theta initial, and I get delta theta is equal to negative 1.57 radians. The negative here is important. I went from this position to this position. That tells me that when something is going clockwise in the clockwise direction, that represents a negative. The delta theta is negative if we go in the clockwise direction. If we're going counterclockwise, then delta theta is going to be positive. And we'll see this again later when we start talking about velocities. To answer the question, what distance did it walk, I'm going to use this equation here, which relates my arc length to my angular position. Okay, or specifically, I can say like delta s, like what's the distance of this arc right here from some initial s position to some final s position. What's this distance? You could just probably look at this and say, well, that's 1/4 of a circle. And the circle has a total length around it of 2 pi r. So I'm looking at 1/4 of 2 pi r. That's fine. Or I can use my angular displacement and my radius of my circle and say that delta s is equal to the radius times that angular displacement, or negative 0.785 meters. This is what you would get also if you just took 1/4 of 2 pi times r. The negative here again means it's clockwise, and we're going to start to get used to that. Negative means clockwise, positive would mean counterclockwise.